Good day, students. Welcome to mathgotserved.com. In this clip, we're going to be going over problems 28 to 32 of the Algebra 2 Trig January 2016 New York Regents exam. All right, let's take a look at question 28. We're to solve it algebraically for x with this given radical equation. So what's the general procedure steps for solving radical equations of this nature? Let's take a look at the steps real quick, and then we'll go ahead and apply it to this problem. So first thing you want to do is isolate the radical expression, okay? Radical expression. In this case, the radical expression that we'll be isolating is the square root of 2x plus 1, okay? After isolating the radical expression, you will try to eliminate the radical by squaring. Okay, so step 2 after isolation is elimination. Eliminate the radical by squaring. Okay, and after doing that, you just basically solve the resulting equation. Solve the resulting equation. This should be easier because the resulting equation will not have any radical components to it anymore. Okay, so let's apply these steps to solving this radical equation. The square root of 2x plus 1 plus 4 equals 8. All right, so let's isolate the radical expression first. That can be accomplished by subtracting 4 from both sides of the equation. That leaves us with the square root of 2x plus 1 equals 8 minus 4 is 4. And then you proceed to square both sides of your equation. On the left side, the square and square root cancel out. That's the objective of squaring both sides of the equation because the inverse of the square root function is square. So when we have that cancellation action happen, we'll be left with 2x plus 1 equals 16. We have accomplished step 1 and 2, isolation of the radical and elimination of the radical. Now to finish it off, we can clearly see that this is an easier problem. We'll simply subtract 1 from both sides and divide by 2. Okay, let's go ahead and do that. Subtract 1 from both sides, and then you're left with 2x equals 15. And then you proceed to divide both sides by 2. And your final answer is going to be x equals 15 over 2. Okay? So that's that. Okay, let's take a look at question number 29. We're to factor this polynomial expression completely. Okay, so one caution you want to keep in mind, okay, which is that only difference of squares may be factored. Okay, so what does that mean? It basically means that, for example, if you have a square, take out the parentheses, if you have a square minus b square, since this is a difference of squares, it can be factored into a minus b times a plus b. Okay, so the difference minus of two squares is factorable. On the flip side, if you have a sum of squares, a square plus b square, this is prime. It cannot be factored using real numbers. If you want to factor it, you have to introduce imaginary numbers, okay? So this is the appropriate form of a factorable binomial expression in the quadratic form, okay? All right, so let's keep that in mind. Now, if we want to factor this completely, what we'll notice is that we have 4 terms. Whenever you have 4 terms, you want to attempt to factor by grouping, okay? So what I'm going to do is I'm going to split it down the center. From the first two terms, I will factor out the GCFs. The greatest common factor of x to the third and x squared is the variable term with the lesser degree of the two, which is x squared. So when you factor out x squared from x to the third, you're left with x, because x squared times x is x to the third. When you factor out x squared from 3x squared, you're left with 3. Okay? Let's now shift our attention to the two terms on the right side of our partition. So what we're going to be looking for here is the GCF. Okay, so what is the GCF of 2x and 6? The GCF is 2. So we factor out a 2 and we're left with x plus 3. It is as though these two terms were divided by 2. Okay. Now, we're going to factor out the common factors from these two sides of our expression. X plus 3 and x plus 3 are common, so what do? We factor it out. We have x plus 3. After factoring that out, we're left with x squared plus 2. Group those together in their own parentheses, x squared plus 2. Okay, so the factored form of the original expression is x plus 3 times x squared plus 2. Okay, so there goes your final result. All right, let's take a look at 30. In this case, we're solving algebraically for x in this given logarithmic equation. So one thing you want to recall is one of the properties of logarithms. Okay, so you want to recall that if you have b raised to the log base b of x, this simplifies into x. The reason is because the inverse of exponent is logarithm. So when you take the power of a base, log with the log of the base identical to that base, what happens is that the cancellation action happens, and you're left with the logarithmic argument of the power that's a logarithm. Okay. Also, if you switch the order, let's say you are taking log base b, and then your logarithmic argument has a base that matches the base of the logarithm. So let's say the argument of your logarithmic function here is b to the x. Because log base b and b to the x are inverse functions, what happens is that log base b and b cancel out, and you're left with what? You are left with x, just as was the case in the first property. Okay, so keep that in mind. We're going to be employing just one of these properties in solving this equation. Okay, all right, so here I want to eliminate the log from this equation. It's kind of annoying, so how do we go about doing that? Now notice that the base of this logarithmic expression on the left side is 8. So what I'm going to do is I'm going to exponentiate both sides of my equation using 8 as my basis of exponentiation. Okay, so put a big 8 on the left side and a big 8 on the right side. On the left side, you put a little log base 8 of 16. Okay, so that is equal to, on the right side, a little x plus 1. So I just exponentiated both sides of my equation with 8 as the base. Okay, so what the mistake a lot of students make is that they forget to exponentiate the right side. So if you exponentiate just one side, what you're doing is you're changing the problem. Okay, so you don't want to do that. You want to preserve equality. On the left side, what happens? You see the first rule we went over manifesting itself here. 8 and log base 8 are inverses, so those two cancel out, and you're left with 16 is equal to 8 raised to the x plus 1. Now, when you're solving exponential equations, which is the case here, if you can get the bases to match, then you can basically eliminate the bases and equate b powers. Okay, so can I write 16 as a power? Absolutely. 16, if you break it down, 2, 8, 2, 4, 2, 2. 16 is 2 to the 4th power. How about 8? 8, 2, 4, 2, 2, or you can look at it here. 8 is 2 to the 3rd power. This is excellent because we can express these two bases as powers of a number that is identical, namely 2. Okay, so 16 will now be written as 2 to the 4th power, and then 8 to the x will be written as 2. Now you gotta be careful here. We already have an existing expression for the power of 8, and then you're raising it to the third power. So what you want to do to ensure you do not make mistakes is include that parenthesis there. So that this new power that you're introducing is appropriately distributed up across both terms of this expression. Okay. All right. Now you see that the two 2's match. So you can cancel them out, or you can take log base 2. All you just have to do now is just set the powers equal to each other since the bases are identical. And then you can also, well, let me just show you that intermediate step so there are no confusions. So 3 times x plus 1. Okay. So the two sides of my equation have identical bases, so I can proceed by equating the powers since the bases are identical. Okay. So I have 4 equals, and I'll distribute the 3. You have 3x plus 3. Subtract 3 from both sides. Let me switch my equation around. I'll have 3x equals 1. Then divide both sides by 3. And then we have our final answer, x equals 1/3. Okay, so that is that. All right, let's take a look at question number 31. It says, determine how many 11-letter arrangements can be formed from the word cataragus. So this is a distinguishable permutations problem. Okay, so let's go ahead and write down the formula real quick for distinguishable permutation. Remember, permutation basically means arrangement, okay? All right, so the formula is as follows. The number of arrangements of the letters of a word with p letters, or a p letter word, is equal to p factorial, or a p letter word with, let me put in some more information, with one letter, with the letter repeated r times, another repeated s times, and so on, okay, is given by p factorial, the total number of letters factorial divided by r factorial times s factorial, and then the pattern goes on, okay? So you take the total number of letters, you find out the permutation of that divided by the product of the factorial, the product of the factorial of the number of times that letters are repeated in that word. Okay, so that's how you carry out, you calculate distinguishable permutation. Okay, so let's go ahead and write down what, write down the word first. So I like to stack it up vertically. So we have C-A-T-T-A-R-A, cataragus, GUS. Okay, and I count the letters again just to make sure that it's 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Uh-oh, I have a problem here. I did not spell it correctly. It's RAU. So RAU GUS. Perfect. So it's always good to count so you make sure you don't make any mistakes, okay? Now, we have a total of 11 words. So total of 11 words. The problem told us initially that's an 11-letter words. Now I want to count the repetitions, okay? So I look at C, I have, how many C's are there? One, there's just one C. Okay, so we have one C. And then A, 1, 2, 3. We have 3 A's. How about T? 1, 2. We have 2 T's. How about U's? Another R. R, we have 1 R. How about U's? 1, 2. We have 2 U's. How about G's? We have 1 G. How about S's? We have 1 S. Okay. Now, what I care mostly about are the words that repeat. Okay. The words that repeat are my A's 3 times, my T's twice, and my U's twice. Okay. So in this case, this would be basically my R, this would be my S, and this would be my T. Okay, so number of arrangements is going to be given by the total. So we have 11 words, so 11 is equal to P. Another way you want to check to make sure that this setup is here is correct. Out of these numbers, 1 plus 3 is 4 plus 2, 6 plus 1, 7 plus 2, 9, 9 plus 1 plus 1 is 9 plus 2, which is 11. Perfect. So number of arrangements is P factorial. Let's change the color of that. Is P factorial the total number of letters factorial divided by the product of the factorial of the repeated letters. In this case, we have R factorial, S factorial, and T factorial because we have 3 letters that repeated themselves in the spelling of this word. Okay, so P is 11, so 11 factorial divided by R factorial, which is 3, times 2 factorial for the T's, and then times another 2 factorial for the U's. Okay, now let's compute the value of this expression. There's a number here with our calculators. Now you want to be really careful. Okay, whenever you have multiple terms in the numerator or denominator, you want to communicate their grouping format to the calculator by using parentheses. Okay, so we have 11 factorial. Where's my factorial symbol? I'll just go to the catalog because everything is there. So let's go there. Catalog, go up. I'm scrolling. Oh, there you go. Okay, so enter. So 11 factorial divided by parentheses. Now you have 3 terms here, so you have to basically group them together so that the calculator can know exactly what you're saying. Okay, so the calculator cannot read your mind, it cannot see the problem you're trying to solve. So you have to endeavor to communicate with it correctly so that it gives you the correct answer. Okay, so 3 factorial, 2 factorial is just 2 times 1, but let me put it in so that you see that the answer, what the calculator has to say. So 2 factorial, go scroll up, scroll up, scroll up, scroll up, scroll up. Enter and another 2 factorial. Okay. The nice thing about catalog, button is that it gives you access to all the functions in your calculator. So put that together until your answer is 1,663,200. Okay, so the number of distinguishable arrangements are 1,663,200 arrangements. That is your final answer. A lot of unique arrangements that can be formed using the letters of that word. All right, let's take a look at number 32, the last in this review installment. It says, express negative 130 in radian measured to the nearest hundredths or two decimal places. Now, one thing you want to recall is radian, doesn't matter the order, I'm just writing the list, okay? So radian, degree angle conversion, radian to degree angle conversion, can be achieved by by multiplying by a certain number. Okay, this can be achieved by multiplying by pi over 180 degrees or 180 degrees over pi. So it depends on where you're at and where you are going. Okay, so in this case, we are going from degrees to radians, so negative 130 degrees. Now I have to multiply by one of these two conversion factors. So am I going to pick the first or the second? Now this is the trick. You want the degree unit canceled out, okay? And you want the radian units to remain. So technically we have a rad here and you have a rad here. Now since this number already has a degree in the numerator, you want to pick the conversion factor with the degree in the denominator so that the degree units cancel out. Okay, so we're going to pick the first option that's more appropriate. Why is that appropriate? Well, notice this, pi radians. The degree is in the denominator, which is exactly what we want. Okay, so the degrees cancel out. We can also divide by 0. I'm sorry, divide by 10, you can't divide by 0. So divide both sides by 10, which results in the cancellation of the zeros. So we have negative 13 pi divided by 18 radians. Okay, is this the final answer that we need? No, we were asked to round to the nearest hundredths. Okay, so we just have to plug this into our calculators and then just count it up to two decimal places. So negative 13 pi divided by 18 gives us negative 2.2689. So it's negative 2.2689. We want to round to the nearest hundredth, so we round into the second decimal place. So you look at the number behind it and ask yourself, am I rounding up or just truncating it away? Well, since 8 is 5 or greater, we're going to be rounding up, right? We're going to add 1. So our angle measured in degree format to the nearest degree, nearest hundredths, is 2.27. Okay, so there is the answer for problem number 32.